be talking about mastering Java performance from monitoring to profiling. So hopefully you still remember me. I'm Lennart and Wolde, software engineer at Chillit. I was here at the keynote today, and I talked about the same subject, but more like the why is this a problem that affects most applications perspective, rather than the what can you do about it perspective. And that's what I'm here to do today. So, I'll leave the introduction short, and we have a lot of things to talk about, so I think it's going to be interesting. There's something for everyone here today, but it is a lot of information I'm going to tell you, so not everything might resonate with you. I'm going to start talking about some more informational stuff, and then as we progress through this talk today, it's going to get more and more technical, so I really think there's going to be something for everyone here. And I'm glad to see so many faces around. Thank you so much for coming to my talk. And let's begin by doing a very short recap on the keynote that we did earlier today, where I mentioned this little pyramid that I made with my amazing graphic skills. I think this is a really good way to represent categories of bottlenecks in a sensible way. In a pyramid where at the top you have the CPU, this is where you think your bottlenecks would be because the CPU is running your code. And so if your code is slow, it means the CPU isn't running fast enough. But very often we find that, like I said, it requires some data. So this data has to come from cache or RAM or disk or network round trips, and these are much slower. So if there are bottlenecks in this area, you're going to notice them much quicker. And by the very nature of how it works, then the other things are not really your bottleneck. They're only bottlenecks if the layers below are solved. So I think it works a little bit like this. And I'm going to explain this to you with some information about each of these different categories, and then I'm going to come back to this graph, and hopefully it will land a little bit more. So to begin at the CPU, right? I would really like to, but I'm not going to go into detail in how it works, although I think it's very interesting. But the basic idea is when code is running, it's running instructions. In Java, we use opcodes, right? Your bytecode. But ultimately, it's converted into instructions your CPU runs, which it runs in a cycle. And if you've ever heard the term gigahertz, that's referring to the amount of clock cycles of your CPU. And this is the CPU clock. It fetches the instruction, decodes it to figure out what it has to do and what module has to do it, and then executes it. And it continues like that again and again and again, going down a list of instructions. Except not really. Because most of the time, your CPU wants to do something, it wants to execute, but it can't, and it enters what's known as a stall. A stall means, I want to run, but I'm waiting on data. And I think this is where, from the perspective that I've drawn out in the pyramid, bottlenecks begin to form. So maybe the CPU is unable to do its work because it has to wait on some data that you're trying to load from memory. And this will either come from your cache or your RAM. So the cache is inside of the CPU or even inside of the CPU core. And it's very fast, so it can be less than 1 nanosecond, so almost as fast as a single clock cycle, but it can also be over 100 nanoseconds if it has to fetch it all the way from RAM. And the CPU tries to predict what data you're going to require and put it in the cache in advance so that the chances that it's going to have a cache miss and have to do a really slow retrieval from RAM, right, 100 nanoseconds, crazy, super slow. It wants to limit that as much as possible because in that time it could be doing hundreds of different instructions. But still, we're talking about nanoseconds, and although this is a very interesting area of optimization, it's completely insignificant when compared to networking I/O, because you're speaking of many orders of magnitudes longer latencies when it comes to that. And so for that reason, the optimization on cache utilization is mainly targeted by hardware manufacturers, so the actual people who build the CPU. They design the CPU to be smarter in populating its own cache. And the compilers. So your Java compiler, the Java virtual machine, tries to optimize this as much as it can for you. Your C compiler, C++ compiler, And sometimes we can do this as programmers too, but I think those are edge cases. I mean, of course, it depends on the industry that you're in, but assuming that you're just making general applications, as I assume most people at JSpring are, these are edge cases. But what about disk and networking I/O? Well, now we're speaking about data that is not connected via copper wires, data that's sometimes on a completely different system or a spinning disk. It can be 1 millisecond, a little bit less sometimes for an SSD, or if you're really lucky, a network operation on the same network as you. But very often, because of overhead, 1 millisecond, you rarely see it. Up to as much as 100 milliseconds, rarely more than that. If you are getting network latencies of over 100 milliseconds, find a better data center. But the idea is it's many orders of magnitude slower, because we're talking about a millisecond. So that's one, there's 1,000 milliseconds in a second. Well, there's 1 billion nanoseconds. So you can do a lot of memory retrievals in the time that it takes to do one simple networking operation. And for that reason, this optimization is mainly targeted by application programmers, because we are the ones who program these network round trips in, because we query our database or we call another service with HTTP. And so it's our responsibility to do this, and this is usually where our issues are and where we can make the most amount of improvement. So putting it in perspective again, you have the CPU at the top. You're talking about, and this is milliseconds, 0.000002 milliseconds, roughly, when an instruction is performed. That's pretty quick. And of course, there's way more CPU instructions than there are database calls, but to give you an idea. Cache is still very fast. RAM is still pretty fast, honestly. But then you get the disk and network round trips, and now this becomes an issue, because after just 100 network round trips, you've already spent a second, and a second is quite a long time. So obviously, this is what we should focus on. This is what's running hot. This is where most of our issues are, and this is what's going to have the focus today. Although I do promise I'll throw in a little tidbit at the end about how you can optimize in Java some of the other layers in this pyramid, or at least kind of the RAM cache area. But it's at the end. So what should we do? We know what bottlenecks are. We know which ones we should focus on. But how do we do that? Well, you begin by using metrics and load tests. And these allow you to monitor your application as it's running. So you get stats of your application over time, so you can see what's it doing, which parts of the application are slow. In the keynote, I showed some photos of Grafana, right? It's a very popular visualization platform for visualizing metrics. And if you spend some time to make a good dashboard on Grafana or a similar tool, you have a really good idea when there is a slowdown, where exactly is this occurring. And then the second part is load tests, because knowing when an issue goes wrong, where the issue is one part. But ideally, we want to know, when we build an application, what can my application handle? And in particular, if my application fails because there's too much data or because there's too much request volume, where does that failure occur? So that if it occurs, you know already where you're going to have to solve it. And you also know at which point. So do I even have to be worried about it? Because sometimes, truly, you don't. But more often than not, you do. So what are some good practices here? Well, for metrics, or observability, as it's sometimes called, particularly in relation to doing metrics and also doing your tracing and logging. I think it was JFall, not last year, but the year before, where I gave a presentation about Spring Boot 3, when this particular area they really focused on in that major Spring release. And there's a lot of interesting things now that you can do to implement your metrics, tracing, and logging automatically. So if you're a Spring user, you can always go back and check that out, but it's also pretty well documented at this point. Metrics are key indicators of problems. So they're little bits of information, numbers that give you an indication of how your program is running, and you can use them to identify possible bottlenecks, for instance, by measuring the query duration and the volume. So this is the amount of queries and how long your queries take, and you can do this per query so that if you see the system is slowing down, you know, well, most likely it's a networking bottleneck, like we discussed. So let's take a look at that and let's see which of them is slowing down, if any at all. And you can also take a look at the volume, because maybe the problem isn't that your query is slow, but you're just executing them so often that it ends up becoming a problem. Same goes for HTTP calls. Sometimes we're not querying data from the database, but we want to talk to other systems. Right? This is still a network round trip, and it can be a bottleneck because they can be quite slow. And the same applies duration and volume. And with your metrics, you can create a graph like I did that shows the, both the throughput over time as well as the latency. And with this information, you can get an idea of which part is slowing down the most. And then, of course, another thing that's very helpful is looking at your available connections to the database and your threads. And I'll talk a little bit more in detail about that later. But people also typically will look at error rates. It's not really related to performance bottlenecks, but it's a common metric, as well as machine and JVM usage statistics. So you can see, hey, is my system just being overloaded? Maybe I just have to get more applications running. And the issue isn't that it's slow, but just I need more hardware. And this is an interesting one, because we have a tendency as developers to say, okay, I can't handle any more requests, my service is too slow, I'm going to scale up and get a second server. And this is fine if your server looks like the one on the right. Right? It's hot, it's steaming, the CPU is running hot, you're using up a lot of memory or a lot of CPU, you just need more hardware. Good. But very often, your application is doing nothing, and then pretty obviously, the answer is not to scale up, but to look at why your computer's doing nothing. Why is the CPU not running? What is it waiting on? What are my bottlenecks? And this is, again, why it's so important to focus on these areas first as an application developer. So to get metrics working, typically your application code will use some type of instrumentation API, which abstracts some of these concepts, right? You will typically have like micrometer is, I think, the default in modern Spring, which uses drop wizard under the hood. But it really depends on what framework you use. I'm going to make a bunch of references to Spring, especially later in this talk, but the same concepts really apply everywhere. Where if you can, if something runs for a certain amount of time, you use a timer, because timers keep track of how often something executes, how long it takes. And using that, you can perform some calculations to calculate rates effectively. But you also need a place to store your metrics. So Prometheus, I see a lot. There's other platforms you can use as well. But this is the database that actually stores your metrics. And your instrumentation API can talk to these different backends. Most of them will support almost everything. But that's something you need in place, as well as a place to visualize it, right? So I showed a Grafana dashboard. I think Kibana can also make dashboards for you. That's the place where you use your metrics in order to figure out, well, what do I want to see? Do I want to see how long my database calls take and which ones? Or maybe I want to look at how many threads am I using, or how many tasks are scheduled. Just as many indicators as possible that for your use cases are sensible areas where your application might slow down. And it's a little different for everybody, so I'm not going to get into it too much, also because it's pretty well documented. And you can look some examples up yourself. The dashboard I used in the keynote presentation was actually a template that I modified just a little bit. And one of the nice things is that you get a lot of standard metrics. So if you use Spring, again, or many other frameworks will do this too, you have Spring Boot Actuator, and you get standard metrics about your system and JVM. So here you can see how's my system itself performing. Maybe there's an issue there, but again, usually this is not the case. As well as information about your task executing and scheduling and your data source. So data source means you can see how long does it take to get a first response from the database. So what is the absolute latency to the database? Because that can be a bottleneck. But also, how many connections do I have going out? Because databases can only handle a limited number of connections. And very often we have, and usually this happens without you even knowing it, a pool of connections. 10, I think, is the default in most Spring applications. And once you've used up your 10 connections, you get no more. So this is a very, very common area where things tend to go wrong, and it's a really important one to look at. And I'm going to show some examples about that in a second. As well as your queries, and again, queries, they are just such a common place to get bottlenecks, because if you don't design your query efficiently, it can slow down a lot as your amount of data grows, which is what happened to me. But also, if you're having a batch process, this is an area where you can try to make marginal improvements that end up impacting your performance a lot. And then also the incoming and outgoing HTTP request. But the idea is that if you use a framework, probably all of these metrics are already being exported. You just have to turn it on. It's one setting. Just go into Actuator, go to your configuration, and expose the endpoint, and that's it. Oh yeah, and your message queues is another common area. If you use message queues to communicate data asynchronously between systems, that is another area. And it's a really interesting area, because if a bottleneck occurs in a messaging queue, it occurs not in the sense that everything slows down, but you see them growing. So it goes up, right? You get a backlog of things that have to be processed. But that's interesting, because it's also a really good indicator that there's something going wrong. So this is a really good place to monitor and alert as well, because if this goes up, then concretely there's a big problem. And this too, I'll show some examples in. The second thing you should do is load testing. Now, load testing, you can use a tool. There are many tools available to help you do this. You have Gatling and JMeter. The advantage of using a tool for load testing is that they generate nice reports for you, where you can see how fast your server is. You can see if you've met certain conditions, and you can show them on your demos, and it's really useful. Or you can design your own stuff, and I think particularly this is a good idea if you're not doing standard HTTP APIs, because that's kind of what they're optimized for. Some of these tools do allow you to measure other type of messages, like nothing really comes to mind immediately. I mean, we all use HTTP these days. But for instance, if you have a message that's or a device that's connected with a message broker, and that's your input, and then maybe it's more worth it to design your own system. They look like this. The details here don't really matter too much, but this is what, for instance, Gatling outputs, and why these frameworks can be nice. I don't really like using them too much, but one thing that is nice about them is that they make these reports, and you can use this, and you can keep them over time to get an idea of how your changes affect your performance. And it's really useful for that. So let's talk about some different load tests you can do. One test you can do is an average load test. You try to send load to your service that it's actually, in reality, getting on average. So this is, I'm expecting to get this kind of load, this kind of volume of data, and you just try to accurately represent that and see if it performs within your target. It's useful, and it's an easy one to start with. And if I had done that on the case that I talked about in the keynote, then I would have never run into any issues in the first place. Then you have a stress test. The stress test is more, you try to figure out what your realistic peak load might be. So under the worst possible conditions, what kind of load is my application going to get? That's what I'm going to give to my server, and you see, does it still perform acceptably? Maybe some errors are okay, maybe the response time is a little bit slower, but you don't want it to completely break down. That's what a stress test is for. Then you have a breakpoint test. These are my favorite. They're really fun to do because you're trying to break your own system, so be careful, especially if, I don't know if any of you use serverless features. You know, if you have auto-scaling software, these are dangerous tests. But they're really good to execute because it gives you an idea of at what point does my application stop working. And this will always tell you how much load can I realistically handle, but also when my systems begin to fail, where is that failure going to occur? Do I see any queue going up? Is the connection pool running out? You look at your metrics and you try to find the area where you can clearly say, okay, this is where the issues begin because we've ran out of resources. And maybe it's the amount of threads your application has, maybe it's the amount of connections, maybe it's your queries are too slow, but you try to find that one thing, and that is your bottleneck. And I think this is incredibly nice to know before you send your application out to production, because you know how much can it handle and what is the issue I have to solve before I can have it go up again. And you have a soak test. That means you take your machine and you soak it in some water. No, of course, don't actually do that. This is not professional advice. No. A soak test is just where you try to send some moderate to maybe high load for a sustained amount of time, because you don't want to only know my system performs well for a little bit of time, but you want to know if I keep it going, does everything continue to perform well? If there's potential issues that only occur at certain times because there's a background job that's sending a lot of load to your database, then there can be issues that you might not see if you do a very short test. So a soak test can help you identify those kinds of bottlenecks in your system as well. But I think the average load test is a great point to start. And if you have an application where you think it's useful to know your breaking point, then that's a good one to do too. And you try to keep doing this as you make changes so that you have an idea of where you are with your application. So let's talk about common bottlenecks. So now we go away a little bit from the theory and we focus on some examples that I've seen on what makes applications slow. And I'm going to start with the simple one, database indexes, right? You query data from your database, and it's fast, but you're testing it, and there's only 5 records in your database. Good job. But what when there's 500,000 records in your database? It's not so fast anymore. Well, the indexes you place on your database help you prevent so-called full table scans when you're trying to search for data. So you try to find a mortgage or a property by its address or its name, and because it's sorted alphabetically, it can skip ahead to where it should be, and if it's not there, then very quickly your database can say it's not there, and if it is there, it can give you the record. Whereas otherwise, it would have to check every single record. But it doesn't just stop there. You know, you add a few indexes on the items you search for. No, sometimes you are searching for multiple fields, so you have to create compound indexes as well. This is an index where maybe if you filter by age, so maybe if you filter by date when mortgage was created, and also by its name, and this returns a lot of results. You want to have an index on this because if you don't, and you just only use a single field, then there can still be a lot of results to go through. But also, sometimes we forget that in our queries, we use some type of expression, and then we don't put this in our indexes, because we think of indexes as, oh, this column is indexed, right? So let's say we have accounts, and each account is an email, and we put an index on the email. But when you capitalize your email incorrectly, it still should lock you in. So when you design a query, you lowercase the email, and then you check if the account matches based on the lowercase email. But if you do this, your index is no longer used, because each different capital letter possible combination is stored somewhere else in that index, so it can't use it effectively anymore, or at least not in its entirety. So to fix this, you can also actually put expressions inside of your indexes, and that way it will work again. And a very good thing you can do is most databases will allow you to say, explain or explain analyze this query, and you can tell, are my indexes being used correctly? And also, don't overdo them. Don't make indexes that you're never actually going to use, because indexes do slow down the updating of your records. If you have a big table with 100 indexes on it, but 70 of them are not used, you slow down your writes unnecessarily, and this can cause problems in other areas. So make sure that your indexes are actually used. If you delete code, check that all your indexes are still used and remove the ones that you no longer need. Okay, but what about the queries themselves? Well, first of all, you should avoid excessive round trips. And this is kind of what I talked about in the keynote as well. If you are constantly querying a record and updating it, and then querying it and updating it, and each time you're waiting for the database to give you a result before you continue doing the next operation, then that's a problem. And you can avoid this by using batch select queries to select all the entities you're going to update at once, like this. And it's much faster because the database is doing just as much work, but you're avoiding the overhead of going to the database and coming back each time. So in reality, I found that most often selecting 50 entities at once is about 50 times faster than doing it individually. And it makes sense. But it does increase the complexity of your code a bit because you're thinking about conceptually working on a group of entities now instead of individual ones. So you only want to do this if it makes sense. So it makes sense when you're actually making a batch process. So use batch queries in batch processes. You can also do bulk inserts. You can do this directly in your database client that you use, JDBC, or your database framework. Most frameworks like Spring Data have a save all method that you can use to give it a list of entries that you want to save. But you have to actually go into your settings and tell JPA, yes, when I give you a list of entities to insert them all at once. There's a setting for it. You have to go into your Spring JPA properties and then set the hibernate batch size. In my own test that I showed in the keynote, I did 50. After that, you've really reached a point of diminishing returns, but you can play around with it and find one that works for you. And this is great for batch processes where you're processing a really large list of entities at once. And also, you should use joins correctly. Joins are very effective for one-to-one and one-to-few relationships, but you want to be careful about joining on conditions where there's a lot of possible matches, because you can never put an index when you're querying from one table on a field that exists in a different table. So yes, you can still make sure that the fields that you're filtering on are indexed, but it's going to have to do a lot of smaller searches in place, and this can slow down quite a lot. And sometimes you have to, but try to do this intelligently, because, and that's actually the last point, sometimes it's better to just change your data model. And I'm going to show an example for this in a second. But another thing that you should do is avoid things like wildcard searches. This is very often done for a full text search. It's fine if you know there's only going to be a few records it has to filter. But if there's a lot of them, this is really, really slow. And there's other solutions for full text search. So just avoid that unless you know that the amount of results that you have to filter within your query is very small. So what do I mean when I say change your data model? Well, let's say that you have a list of customers and you have a list of orders and they're connected to each other with a foreign key. And you want to find all customers that have placed an order in the last 30 days. You can do so with a subquery or a join like this. You try to see, I have customers. I want to know which customers placed an order within the last 30 days by filtering on the creation date, which can be indexed. But if your set of customers is very big, and you want to do, for instance, a count to count the number of customers, then it still has to perform a targeted search for each customer in that table. And it cannot simply immediately tell from your index how many of them there are. Whereas if you introduce an extra field or column into your customers table, now you can filter directly. And this is much faster because it can use one single index on your data. But of course, only do this if you need to, because it does add some complexity to your code. And there are some features like computed columns in some databases and materialized views that you can do to do this at the database level. So definitely look into that if you feel that there's really an issue here and you cannot design an efficient query because you are filtering on details in another table. Sometimes it just means you have to change your data or make a second copy of your data, either through a materialized view or in your own code as some sort of a projection. But I feel like if we go any further down into the query world, we're going to be data scientists. So I want to talk about, and this is a very interesting subject, concurrency bottlenecks. And the way I see it is that most of you have worked with concurrency in one way or another, where you have many different threads executing your code. And sometimes we have the tendency to increase the amount of threads, but there's actually a more constrained resource somewhere else that all of those threads are trying to use. Imagine, right, you have a big kitchen, and there's 100 chefs, but there's only one pizza oven. You can add more chefs into the room, but you're not going to get any more pizzas done in time. Probably you'll get fewer of them. So concurrency, how does it work? Well, really quickly in Java, you have executor services. Executor services allow you to dispatch individual tasks, so runnable interfaces, into some kind of queue that is going to be processed by a set of threads. This is usually how you do it. You can also create threads yourself, but it's not really meant for executing short-lived tasks. For that, these constructs are very powerful. So you create one, and you essentially say, I want to be able to do 20 things concurrently. So Java's going to create 20 threads for you. And then you can just 10,000 times execute something. But rather than this executing immediately, let's say you have a function called doSumDBQuery, it's going to do this by adding this into a queue, and the 20 threads in the thread pool are going to take from this queue and process it so that 20 of these things can happen concurrently. And if you have 20 CPU cores, then very likely all of your cores are going to be doing something here. But the number of threads you have can, of course, be much greater than the amount of cores you have, because very often our threads are stuck waiting on something. So we can just spin up a whole bunch more of them. On top of that, we have the completable future API from Java 8. Really nice API. Because when we deal with concurrency, we're inherently dealing with asynchronous tasks, some things that are going to be completed at some point in the future. It creates some difficulty, but the completable future API helps us because we can, it gives us an interface of determining what we're going to do when something is completed. So now we can actually work with results. So let's say you do something asynchronously, and then you want to do something else, and then you want to wait for all of those things to be completed as they run concurrently. Those are the kinds of things that completable future is very good at. So in this code example, again, you create an executor, and in the completable future, all of the functions have an async variant where you can pass in an executor, and that's what it's going to use as its thread pool by saying that when I have to do some work, I'm going to do it by offering it to this queue so that that thread pool that you're passing me is going to be used to process the data. So here, let's say you want to execute 3 queries. If you execute them sequentially, it's 3 round trips happening after each other. So if each takes a second, that's 3 seconds. You do them at the same time, it's just 1 second. And with a thread pool, you can do this and simply say, when all of these things are completed and they're executed on this thread, then join at the end, which means join back, well, it waits until all of them are complete, and your program continues. So going back to the analogy here, you can have a lot of threads, but maybe you only have 1 oven. And if your chefs are the threads, then what is your oven? Well, let's find out. And again, I alluded to this earlier in the talk. Very often, I found it's your database. So if it is your database, then the issue is that your database only supports a finite number of connections. Especially Postgres has issues with this, which is why sometimes people put a proxy in front. But if a connection is really actually doing something, like it's running a transaction, that you need a real connection, and there's just not that many of them. It's a limited resource. So normally, you have some code that's running on your server that wants to talk to the database, so it gets a connection from your connection pool. And it takes this, it does its work, and usually that means either executing a query or running a transaction. And then when it's done, it gives it back so that another thread can then take that and do its own work. And what can happen if you have 20 threads, but there's only 10 connections, or in this case 3, is that the first 3 threads take up the connections, and the others have to wait until they're available again. So now you can add as many threads as you like, 10,000 of them, but if you only have 3 connections, only 3 of them are going to do anything at all. So your program actually gets slower instead of faster. Well, what does that look like? Usually when this occurs, it's something like this. And what is happening here is we're creating a transaction using Spring, and then we're executing some code, where first we're querying some data, and then we're going to submit that by sending it to another service, and that is an HTTP call. The thing is that maybe your query is very fast, and it returns in 5 milliseconds. But if that second line that's executing takes really long, a second or longer, your transaction is still running. So while your transaction is running, the database connection is still needed, so other threads cannot use it. And really, there's no reason to use a transaction here because you're not modifying any data. So if there's an error, you don't have to roll anything back. But very often we find transactions thrown absolutely everywhere in our code, particularly if you use something like Hibernate JPA. So what do? Well, we often see this because we have foreign keys in our code, right? So let's, I was going to go through that line by line. Look at another example where we have a foreign key from, let's say, a property to its occupants. And occupants is a JPA foreign key reference. So if you call get occupants, you get a collection. And this is going to lazily find the occupants of the property by querying all of the occupants by the foreign key constraint that you've defined. And this only works if you're inside of a transaction. Because if you're not in a transaction, the object is not managed, and everyone who's used JPA has probably seen the exception where you try to use a collection and then you get an exception because there's no transaction, so you create a transaction, and now you get more API calls, and now your connections are gone because they're used up by all your transactions that shouldn't even be there. Because if there is no transaction, then a connection is only used for the duration of a single query and then immediately returned. So you can fix this pretty easily. Set the entity graph annotation in your repository. There's also ways you can use entity graphs without Spring Data repositories, but I assume a lot of you are using Spring, so this is just a little example. You can create a new query where you're going to explicitly say, include the occupants for me. They're going to be included now. You can use it. And now you can remove the transactional annotation and perform your API call while another thread has access to that connection again. So that's one thing that's often limiting our effectiveness in concurrency. Because conceptually, if I create twice as many threads to do work, it should be twice as fast. But from the pizza example, sometimes we don't have enough ovens, so we run into an issue. And there's many more that you can reasonably think of. Anything where there's just a constrained resource and you have to wait on that. And you might be like, okay, yeah, but I don't really use these task executors or executor services. But you actually are, and there's a really big piece of code here. This is conceptually how your web server works. So everyone who is using like a regular server application is using either Tomcat or Netty, and they all do something similar, which is essentially this, right? They set up an executor service so they can offload tasks to a thread pool. and then you open on a port, and you say, hey, I'm gonna be taking in a bunch of connections, and I'm gonna do this in a non-blocking efficient way. And then your HTTP server, so for example, Tomcat, if you use Spring, is going to, in a single thread, look at any incoming connection, and then if that is a new connection, accept it. Say, hey, I'm really good, I'm non-blocking, I'm going to register you so that I can process your reading and writing of I/O data efficiently without using up a lot of threads. And then it's going to say, hey, one of my clients is ready to read the data from. It's going to do that. It's going to parse the HTTP data. And then it's going to do something like this. It's going to execute a task asynchronously where your code is going to run. So if you have a REST controller which has some type of endpoint, it's being called from one of these executor services, or very similar, right? Because I didn't actually study the entirety of the source code, but it would work something like that. And then it will also write out responses. But the key point is here, most web servers can read data from all of their connections very efficiently, but eventually it has to execute, and it's going to do that by dispatching to a scheduler. And so when your method runs inside your controller, it's running on one of the, for example, 20 or 50 threads that your HTTP server has allocated. So you are already using concurrency if you use a web server, almost definitely. There's very few single-threaded web servers out there because, you know, it's totally insensible to only accept one request at a time and process it. So if you have a web server, you're already using concurrency, you're already using executor services, and you still have bottlenecks. So pro tip, if you do want to schedule tasks yourself outside of the context of receiving an HTTP request, you can use task executor instead of executor service. It's an old legacy thing in Spring, but a nice advantage of using that is that it has automated metrics as well. So if you use task executor to execute your own task that you want to run on a different thread, then metrics will automatically be published that allow you to see how many tasks are scheduled. So if that queue goes up a lot, then that's probably a bottleneck that you should go and fix. And you can see how many threads are actually being used on average in my executor pool, so you can tune and figure out how many threads you have to use. It's a really nice advantage because you don't have to do anything other than just use task executor instead of executor service. So this is how it works hypothetically, right? Your operating system manages all the connections for you, and it does this very efficiently. Then your web server is going to process all of those in a single thread by using a selector, like what I just showed you. But then they still end up being queued at an executor service, all of the requests, until one of the available threads, here I drew 5, but you're going to have way more than 5 usually, is available to process one of these requests. So this is another potential bottleneck, and you will very often find this if you work with concurrencies. There are queues all over the place because the very concept of offloading tasks to another thread involves having a queue. So these queues, it's important to observe them because let's say your program is really slow, or let's say you're being DDoSed. What's going to happen is that this queue, this executor service queue, is going to grow, which means that it takes more time for your request to be processed by your application. And as a result, your latency is going to go up, and eventually requests are going to be rejected completely because there's too much of a backlog of work. And that's what happens if you don't address your issues. So I'm very short on time, but there's one thing I really wanted to talk about briefly, because we talked a lot about networking and monitoring and metrics and concurrency, but we didn't talk a lot about what Java is doing. I think we have just 3 minutes, because we already spent the 45 minutes, but I'm going to go through this in super speed. But Java is also doing some cool things with improving your memory management, so improving the amount of Well, improving the bottlenecks by having more data be present in the cache instead of memory. So in C, for example, you have an object called book with two properties, and when your program runs, it has a stack which contains all of your variables. It starts with just a stack pointer, and then a number gets added, and then your object is added onto the stack directly. So you get your fields are added onto there directly, and that means that if you access them, they're going to be on the stack. This data is cached. It's very quick, and it doesn't have to do any following of a pointer, because the string, for example, is a car pointer here. That means that if you want to read the characters of the string, you have to follow a pointer, and a pointer can be anywhere in memory. And accessing data that could be anywhere in memory is much slower than accessing data that's close to where you've just accessed data. Because in Java, it's like this. It starts off the same, where the value of your first variable is added into the stack, but then all objects in Java are allocated on the heap, which means it's somewhere random in memory. Not completely random, actually, but for the sake of argument, random. And what ends up being added to the stack is a pointer, so an address, somewhere in RAM of where the data actually is. And this means that this will be significantly slower. And this applies not only to the stack, so to methods that are running, but also to arrays. If you're iterating through an array and the data is all next to each other, it's going to be in the cache and you're going to be able to go through it very quickly, whereas if it's all pointers, it's much slower. And so what Java is doing is they have created Valhalla, which allows you to simply say value class or value record, and now this data can be inserted directly into an array instead of a pointer to a random place in memory. And then if you iterate through it, all the data is there, and it's going to be much faster because now you're hitting the cache layer each time instead of very often hitting the RAM and running into more CPU stalls. There's a lot more you can learn about that, but we're out of time. So I want to thank you all, and I hope you enjoy your day. And come say hi to us at the Chill It stand. We have ice cream and waffles and hot sauce challenges, and let's talk about this. If you have any questions, I'll be there.